Hi, and welcome to Hack in the Box 2021 Amsterdam. I hope you're doing well, and you're excited to be learning about TLS SSL fingerprinting and overcoming it. Today we'll be talking about JARM Randomizer, which does exactly that. So let me start by introducing myself. My name is Dagmawi Mulugeta. I am currently a threat research engineer at Netscope. Previously, I've held positions as a researcher, software engineering, and developer at multiple companies. I have my master's in cybersecurity from Drexel University, and my interests span capture the flags, exploit development, and abuse, and general research of cloud applications as well. Cool. So let's talk about what the rest of this talk is going to be. We will start by, or the goal of this presentation is to talk about SSL and TLS fingerprinting and take a look under the hood of JA3 and JARM. And then we'll talk about how JARM fingerprinting particularly isn't bulletproof as a lone tool. And then we will segue into how miner-side, server-side changes or configuration tweaks result in different JARM fingerprints. And finally, we will package all of this up and present or provide a tool to switch between these configurations to return a different and desired JARM signature. Cool. So let's start by talking about what JA3 and JARM are. To do this, we need to take a step back and talk about the TLS or SSL handshake. So TLS and its predecessor SSL are generally used to encrypt communication between applications like internet browsers and target servers, right? So typically when you type in your username or your password to log into facebook.com, right, this data is passed back and forth in an encrypted fashion. So someone in the middle can't read that data. And this encryption is set up in what's called a TLS handshake. So you have a diagram on the side of what a typical handshake looks like. The client or the browser initiates it by sending a client hello that contains cryptographic algorithms that are supported by the client. These are referred to as the ciphers. Some versioning details about what the TLS handshake should look like. The supported extensions, a list of compression methods, and other session-related parameters as well. In response, the server sends back its own server hello message when a satisfactory set of algorithms have been selected and they've been confirmed. Subsequently, after doing all of this, the server and client will proceed to verify each other's authenticity via digital certificates and derive session keys to tunnel the remaining traffic in an encrypted fashion. Now, one thing to note, these packets are heavily reliant on the packages and methods and operating systems that are used to derive it. So when building these applications, the selected packages in the libraries and what platform we choose to run our application on severely influence these parameters in these packets. Cool. So let's talk about what JA3 does now that we know what the TLS handshake looks like. So JA3 was a tool that was introduced by Salesforce in 2017. And the goal is really to fingerprint these TLS Client Hello packages, right? So that first initial bit of that TLS handshake where the client sends its client hello message, we want to fingerprint those. And we will look at specific fields in that TLS client hello packet. And these fields are the TLS version, the supported ciphers, the extensions, right, the elliptic curves or the supported groups, and the elliptic curve point format. So these 5 fields are what we grab out of these TLS client hello packets, and then we will aggregate them together and hash to produce that final fingerprint. And the reason we did this is it's quite useful to identify unusual clients within a network. So by taking these fingerprints, we can actually group client applications like Google Chrome browsers and Internet Explorer browsers and your system, like clients like Slack and all of these things can be grouped together within a network by just fingerprinting this portion of that TLS handshake. So now that we've talked a little bit about what JA3 does, let's talk a little bit about what JARM does. So JARM, as opposed to JA3, is a server-side fingerprinting technique, meaning that JA3 was used to passively fingerprint client-side applications by looking at specific fields in their TLS Client Hello packets, JARM is an active fingerprinting tool that reaches out to servers and grabs their server responses, meaning they'll grab their server hellos and fingerprint or grab certain fields from those server hellos and fingerprint those fields to identify that the hash or the fingerprint for a specific server. So it's used to fingerprint server hellos in the SSL handshake. So as opposed to the 5 fields in the TLS Client Hello packet or in JA3, in the server-side hello packet, JARM just looks at 3 fields: the TLS version that gets sent back, the cipher that was chosen by the server to continue the rest of the handshake, and the TLS extensions that are supported as part of that server hello response. So let's talk a little bit about how JARM works. So JARM works by actively sending 10 customized TLS Client Hello packets to a target server and then capturing that server's responses. And these Client Hello packets are specifically designed and engineered to draw out the most unique responses from a target server. So asking it questions like, does this server support TLS 1.3? If we order the ciphers a specific type of way, which cipher would it pick? What if we shuffled them around and maybe even dropped some? Which cipher would it pick then? So asking it questions like this, grabbing those responses, and then aggregating them together to give that JARM fingerprint is the process it follows. And we can see the configuration selected for these 10 TLS Client Hello packets in the PyJARM implementation on the slide. So PyJARM is the Python implementation of JARM that was open sourced by Palo Alto Networks. And we can see the kind of the nature of these configurations for each of these Client Hello packets that get sent out. And after grabbing all of these responses, it aggregates it together or JARM aggregates it together to give a fingerprint. So what exactly is this fingerprint? This fingerprint is actually a fuzzy hash fingerprint that is made up of 2 consecutive 30-character and 32-character blocks. The first 30-character block is actually the TLS version and the cipher for each of the server hellos that got sent back. So each of these 3 characters represents that one response for that specific hello packet. And the second block is the SHA-256 hash of the TLS extension. So this is a truncated version. It's not the complete version, but that makes up that second block. And then when you concatenate these together, you have that 162-character block that is the JARM fingerprint. And you can see the figure in the slide for where that line is drawn for a few different domains that were fingerprinted using JARM. So what JARM is used for, and now that we see in that picture, right, it's useful for 2 things. The first is we can group servers together by configuration. So as you can see in the slide for Google, YouTube, and Blogger, that JARM fingerprint is actually the same. And this is because the infrastructure for these, or the underlying operating system and application that these servers run on top of, are actually similar. So we can group these servers together. We can say these group of servers belong to Google, and these belong to Netscope, these belong to Apple, etc. And the second is we can identify malware command and control infrastructure. In popular attack frameworks like Cobalt Strike and similar C2 infrastructure that's normally very difficult to detect and defend against, we can easily identify using a fingerprinting technique like this, like JARM. And the rest of these presentation will be focused on JARM. We'll touch base with JA3 a little bit later on, but most of the work we're doing here and the research is around JARM. So what are some challenges with using JARM? What are some weaknesses with this implementation that you need to keep an eye out for when you run a JARM scanner or JARM fingerprint in your defenses? As we mentioned earlier on in the presentation, JARM and JA3 and TLS fingerprinting is very much tied to the operating system, the packages and libraries, and other custom configurations of the server-side application. For example, Cobalt Strike JARM is actually the JARM for Java 11 TLS stack. So when we're on the internet and we're trying to identify Cobalt C2 infrastructure and we identify the Cobalt Strike C2 JARM, we're actually identifying that Java application that's running on that specific package or using that specific package. So when would this cause issues? Firstly, when you're using it by itself, it can cause a few detection issues. Firstly, there can be a higher rate of false positives. As we shown in the example above, it can be quite difficult to identify exactly what we're looking at as opposed to the framework infrastructure or framework and operating system that it's running on. And this is especially enhanced when we're looking at common libraries or tools that use common libraries and operating system sockets for communication, because you're pushing that further down, which makes it a little bit hazy to identify. Secondly, we can see that switching some configurations around, or maybe using a proxy or a load balancer, would result in a completely different fingerprint, which makes this even more unreliable when it's using it by itself. Although JARM plus other intelligence has been proven to be quite useful, it is as part of a grouped detection scheme, as part of a grouped approach. So while it's not completely trivial to get a new JARM fingerprint, as opposed to mechanisms like the user agent string, which is just a header in the request you can change, JARM by itself is actually not bulletproof as well. So now that we've talked a little bit about what JARM is, what the weaknesses and challenges are, and how it works, let's talk a little bit about how these server-side changes or these server-side tweaks, specifically a TLS version and the cipher supported by the server, would affect the overall JARM fingerprint. So this was a test that was run on a Mac OS system using PyJARM for fingerprinting. PyJARM is a library implementation of JARM that was introduced by Palo Alto Networks. And what we did was we used the SSL library in Python to cycle through the supported TLS versions and ciphers, and we spun up a server and we fingerprinted that using JARM, or PyJARM, and we tried to see what the resulting JARMs were. And as you can see from our findings, changing the TLS version and the supported cipher server side actually changes the JARM fingerprint a decent amount. So how can we use this to evade JARM? Now that we know that changes in server-side configs can actually result in a completely new fingerprint, how can we use this knowledge as a red team operator or a penetration tester to give ourselves the upper hand when evading JARM fingerprinting? So before we get into evading JARM fingerprinting, let's talk a little bit about JA3 Transport. JA3 Transport was presented in 2019 by the CU Cyber team, and it's a Go library that's specifically used to evade client-side JA3 fingerprinting. So if you remember from our initial presentation of JA3, JA3 is used to passively fingerprint Client Hello packages to identify what kind of application made that request. So things like your browser versus a Slack client or some malware that may be on your system, right? JA3 can be a really useful tool to fingerprint and identify these client applications. JA3 Transport is a library that you can incorporate in a Go executable or a Go binary to evade this kind of fingerprinting. In this talk, we'll present JARM Randomizer, which is the server-side. You can really think of it as the server-side equivalent for JA3 Transport. And it achieves evasion by cycling through these supported configurations to give the desired JARM fingerprint for red team operators and penetration testers. So let's talk a little bit about JARM Randomizer itself. At the heart of it, it cycles through the supported configuration server side to enable a different fingerprint or a different desired fingerprint for the operator. Some dependencies are pipenv. It's written in Python 3.9, so you need to have that installed when you run this. PyJARM, Shodan, and PyBinaries are also required for additional functionality. So the current features for this tool are to iterate and identify valid configurations during setup. So this is really useful, so you don't have to do that footwork yourself. Secondly, it'll check the generated or the valid JARMs for your system on binaries and Shodan to give you some more insight on the usage of the specific JARM that you want. Thirdly, you can cross-check these specific JARMs against a known red team tool list to make sure that you're not using the ones that have been associated with public command and control tools. And finally, it gives you the ability to cycle through or rotate configurations at specific intervals so you make sure you have a different JARM fingerprint at the desired time interval. So where is the placement of a tool like this? So really, it is a Python proxy that is meant to be placed in front of a command and control server. So as you can see, without the randomizer, this would be what a typical deployment would look like in an engagement. With the randomizer, you'd put this Python proxy on the same system or a different system that's in line with that traffic, right? And you can use this alongside Cobalt Strike to evade fingerprinting of the Cobalt Strike tool itself. You can use JARM randomizers to cycle through these configurations. So let's talk a little bit about the setup process and what this tool gives you when you do that setup. The setup is actually required for this tool to run, so it can identify the supported configurations on the system, and it also helps you lay that kind of groundwork that's required to run the proxy successfully later on. And what it does is, the first thing is it grabs those list of ciphers that supported on the system, right? And then it finds all the possible JARMs by rotating through the TLS versions and the supported ciphers, and it validates them. And once it validates them, it tells you how many JARMs that it found that it can support on the server side and how many TLS cipher pairs generated those JARMs. And if you've supplied an API key for binary or Shodan, it grabs those metrics for the JARMs and the usage on the internet, and it'll give you some statistics on that as well. And once it's laid all this out, it'll give you the command you need to run so you can have that proxy deployed and ready. So let's talk a little bit about one test run on a Mac OS system. And let's analyze some of the findings. So on a Mac OS system, we identified 31 possible JARMs across 48 TLS cipher pairs. And in this table, we can see the top 5 JARMs when sorted by occurrence in Shodan, right? And we've also co-referenced or correlated the JARM fingerprint against the known list of red team tools from a publicly available repo to grab that usage as well. So the important things to note here are 2 TLS and cipher pairs can generate the same JARM. As you can see, for the 5th entry, 18 TLS cipher pair instances actually generated the same JARM fingerprint. And while it might not be completely obvious here, because this is showing the top 5, but if you saw that complete list, there is a sway towards Python product. And lastly, you can see that second JARM field actually matched 5 red team tools. So as a red team operator, you might want to keep that in mind and maybe avoid that specific entry to maintain operational security. And all of these, the binary edge, Shodan, the red team tools are all supported by the randomizer itself. So these are statistics you can pull out if you wanted to run this on your system and get some stats back. So let's talk a little bit about the two use cases that we feel the field really benefit from. There is a configuration file present in that repository, so if you wanted a specific configuration, you can achieve it. But these are the two that we feel are very important for people in the field. The first is to serve one preferred JARM. So you've done that analysis that we saw in that previous slide, and you found that JARM fingerprint that you want to run that meets your criteria for operations. So you can grab that configuration, set it in that configuration file, and it'll run for that JARM fingerprint for as long as you want. The second is maybe you want to cycle through these configurations every 5 seconds or every day or every month. You can set that in the configuration file as well, and it'll cycle through these supported configurations with a little bit of downtime to swap out or restart that server, and you'll have that a new JARM that's supported on your system as well. So what are some limitations from using this tool? One, there's a finite number of signatures. Like we presented earlier, and we've talked about many times in this presentation, these fingerprints are very reliant on the underlying operating system, the packages libraries. So you will not have that infinite space where you can generate that specific JARM that you want. You are limited by the signatures that are supported on your system, right? Secondly, the client compatibility check is very much required. So what we've done here is, or in the setup process, we've checked the server. The server has checked whether it can negotiate a successful handshake itself with a server that it stood up. And if it passes that check, then we give that a check mark for those configurations. But you also want to make sure that the client you're packaging and deploying on these red team engagements or these penetration test assessments, you want to make sure that client can also successfully make a handshake with the Python proxy to make sure there isn't an issue setting up a connection there. Thirdly, JARM Randomizer does not make any changes or have any type of support to mangle the traffic itself to avoid detection, right? So the traffic itself might be identified by other behavior-based methods or other C2 traffic identification methods. And lastly, and this is the most important one, this is not exhaustive yet. Right. We have done a decent amount of work here, but it's not complete. This is meant to be a step in the direction to fully evade fingerprinting. And we feel that this is important enough to share with the community, but there's definitely a lot more work that needs to be done here. Right. And some of the work that we'll do to improve this is one, we'll scale to generate a larger list of signatures for sure, to tackle number one. Secondly, we would like to have functionality where you can just point this at a server and say, I want that server's JARM, and you can achieve that configuration as well. And lastly, we're trying to come up with, and this is more on the defensive side, we want to come up with a TLS-based fingerprinting technique that is more difficult to evade than JARM and J3. And both of these are amazing to include. Are great to include as part of your tooling infrastructure, and we want to add on and improve these as well. Finally, we want to give amazing recognition for the Salesforce engineering team for JA3 and JARM. They have done an amazing job at identifying these phenomena and packaging them up or releasing them for the community. And they also did a great job of documenting and coming up with cool GIFs as part of their blog, which I shamelessly borrowed for this presentation. And the CU Cyber team for JA3 Transport, which these two teams really kind of laid out the groundwork to do this project and bring JARM Randomizer to you guys. And in the spirit of matching JA3, JARM, and JA3 Transport, we are open sourcing JARM Randomizer, and we hope you guys take it, play around with it, make changes as well. So let's talk a little bit about what the takeaways are, and we can conclude this presentation. So the takeaways are, first, the JA3 and JARM. What are they? how we can use these in our systems, how they work, and talked a little bit about the background for these. Secondly, we talked about how JARM is really not reliable as a lone tool by itself to fingerprint these servers, right? Thirdly, we showed that just minor server-side changes and configuration tweaks actually result in different JARM fingerprints. And finally, we packaged all of this up and presented it as JARM Randomizer, a tool that you can use to cycle through these configurations, and red team operators and penetration testers can actually use to maintain operational security. And finally, this is an active area of research that we very much are involved in. So keep an eye out on our blog for the latest from our research and tools and other interesting stuff as well. Finally, if you need to follow me, reach out to me, message me. That's my Twitter handle. My LinkedIn is right there. GitHub link will also be available for you guys. So feel free to reach out on any of these. And if you want to keep up with us and what we do here at Netscope, follow our blog and see what cool stuff we have. Awesome. Thank you very much for your attention. I hope you got something out of this presentation, and I hope that you enjoy the rest of your time here at Hack in the Box 2021 Amsterdam.